Hello everyone. Today we're gonna be talking about system of linear equations. We're gonna start with two very basic methods that I believe you guys learned already in college algebra. So let's tackle the two sections by examples. So start with system of two linear equations with two unknowns. Example. Solve for x and y. 2x minus y equal to 5, and the second equation is x plus 3y equal to -1. Okay. So this we call system of two linear equations with two variables or two unknowns, x and y. Before solving, let's explain the idea of the name of it. It consists system because we have more than one equation. And here, in this case, we have two equations. Two variables, of course, is x and y is obvious. Why is it linear? Well, you can think of it this way. For now, it's like each equation, if you can graph them, it's an equation of a line. So that's why we call linear. But later on, we may have three equations, three unknowns, four unknowns. It turns out that the graph's not a line anymore. So technically, linear is something like flat. And here, you have just variable times the coefficient, no x squared, no x cubed, same thing for y, no y squared, no y cubed, no square root of y, and those, or no y denominator for the fraction. It's called linear. Okay. So let's start with the basic method, the first basic method to solve, called substitution. Okay. First method, substitution. The idea of a substitution is what? We're gonna choose an equation. We're gonna solve for one unknown. So of course it's gonna be depending on the other unknown. Okay. So make it easy. Let's label or name those equations. Let's go equation number 1. The second one, let's call it equation number 2. So it's our choice to choose an equation and then solve for one unknown that we like. So be smart, choose an easy equation and solve for the easy variable that you like. Okay. So in this case, how about choose equation number 2? Any equation you like. Okay. Choose an equation. So I choose equation number 2. And I solve for x then. Because all I have to do is just subtract 3y's on both sides and I have x in terms of y. So I got equation 2, x plus 3y equal to -1. Subtract the 3y on both sides. I have x equal to -1 minus 3y. Okay, x in terms of y. Now, what we're going to do next is we're going to plug that x by -1 minus 3y into the other equation. I used equation 2 already to solve x. I have to substitute that into equation number 1. So let's call this is step number 1. Step number 2, substitute x equal -1 minus 3y into equation number 1. So equation 1 is 2x minus y equal to 5. Now it becomes 2 times -1 minus 3y minus y equal to 5. You see what I've done from the first line and second line in here? Whenever I see an x, I replace it by -1 minus 3y. I have this. Now we simplify. We can solve for y. -2 minus 6y minus y equal to 5. -2 minus 7y equal to 5. Alright, so add 2 on both sides. -7y equal to 7. So y equal to -1. After having y equal to -1, we plug it back to either equation 1, equation 2, or the equation that we have from step 1 right here. You can solve for x. So x equal to -1 minus 3 times y, which is -1 minus 3 times -1. It's -1 plus 3, so x is equal to 2. And this is how we usually write to express our solutions. X comma y is equal to 2 comma negative 1. It's like a 2 tuple. Alright, that means x equal to 2 and y equal to negative 1. It looks like what? A point. X coordinate and y coordinate of a point on the plane. Alright, so the solution is x is 2 and y is negative 1. Alright, so graphically, let me just extend the concept a little bit more, not just a technique to solve, but explain the idea behind the litho. Graphically, what does it mean by solution? As I explained before, if you have two linear equations, it's an equation of a line. So actually, the first equation is a line. Okay, and similarly, second equation is another line. Alright, so all the value x, y satisfy the first equation will stay on the first line. All the point x, y satisfy the second equation is staying on the second line. And solving for system linear equation means you're looking for all the points that satisfy both lines or stay on both lines at the same time. Of course, if a point staying on both lines, it's going to be the intersection. Okay, and this intersection in this particular example is 2 comma negative 1. Right, and that's why we usually use a pair of numbers to represent solution. Okay, so actually in this system right here, you got exactly one solution because two lines intersect each other at one point. Okay, if you have this in mind, there are other cases that you may not have any solutions at all. That is the case if the two lines are parallel, means they have the same slope and different y-intercept. They never intersect each other and keep the same distance from each other forever. Okay, or you may have more than one solutions. You have infinitely many solutions, and that is the case that the two lines are on top of each other. Okay, so in this case you have what? Infinitely many solutions, because how many points of intersections? Infinitely many points. Okay, the system right here is a conditional system. You have one solution. This system right here is usually people cause a contradiction. You have no solution. And the system right here, you say what? An identity, because you have a lot of solution. And the two lines actually the same. So let me give you an example. This one is right here already. Parallel lines, think of it. Say 2x minus y equal to 5. How about the second line? 2x minus y equal to 1. You guys see that? How in the word 2x minus y equal to 5 and then equal to 1 at the same time, unless 5 equal to 1. But that's not happening in real number system, so no solution. And here, have this. 2x minus y equal to 5. Second equation, watch. 4x minus 2y equal to 10. You guys see how I get to the second equation? I actually just multiply the first equation by 2. So I have the second equation. It looks different, but actually, technically, the two equations are actually the same. All right. Here, one solution, no solution, infinitely many solution. All right. And this is conditional system. This is a contradiction, and this is an identity. Okay. Oh, by the way, if a system has solution, that we say that the system is consistent. And if the system doesn't give you any solution, we're gonna say the system is inconsistent. And this one is a consistent system, got a solution. The last one right here is also consistent because you can find a solution, right? Many. This one is good. And the middle one is inconsistent because you don't have any solution from it. All right, so pretty much that's the idea. Let me move on to the second method of solving for a system of linear equation. It's called elimination. All right. Of course, you should expect we have the same answer, just a different way of tackling the problem. All right, second method, elimination. All right. You guys see that the way we organize the two equations, x goes with x, y goes with y, and equal sign and number goes with number. And we see this right here. If we multiply the entire equation by a constant, and the equation pretty much the same or equivalent to the original one. So Let's bring up the idea. Say if I multiply the first equation by 3, you guys see why I think of 3? Because if I multiply the first equation by 3, I'm going to have what? Negative 3y in here. And after that, if I add the two equations together, what happens to the y? It is eliminated. And that was the idea of elimination method. So let's try it. Take equation number 1. 1 multiplied by 3. We have what? 6x minus 3y equal to 15. Keep in mind that you got to multiply everything by 3, okay? The second equation, I'm going to keep it the same. X plus 3y equal to negative 1. Now I'm going to add the two equations together. And you guys see what happens to the y. It's eliminated. I got 7x, negative 3y plus 3y is 0. And 15 minus 1 is 14. Of course, x equal to 2. Okay? And of course, after having x equal to 2, you can go back to substitution, plug x equal to 2 into either one of those two equations. You can solve for y. Or you can even do elimination again. Last time I eliminated y, right? Solve for x. Now I can eliminate the x, solve for y. How do I eliminate x? I multiply the second equation by negative 2. You guys see why negative 2? So that I got the opposite of 2x up here. When I add the two equations together after multiply by negative 2, the x will be cancel out, and I can solve for y. So let's do that. Equation number 1, 2x minus y equal to 5. Equation number 2, I'm going to multiply everything by negative 2. Let's write it down a little so I got more room to write. 2x minus y equal to 5. Equation number 2 is, after times negative 2, we have negative 2x, negative 6y equal to 2. Negative 2, negative 2 times 3, negative 6, negative 2 times 1 is 2. Now add them up. X cancel out. This is negative 7y equal to 7. Of course, y equal to negative 1. You guys have the same answer. Alright. So in here, I'm showing you guys two methods to solve a system of linear equation. It's up to you to choose whatever method you prefer to use in your actual exercise. I claim that sometimes substitution turn out to be better, means faster, easier to solve. Some other time, elimination turn out to be better. So it's up to you to choose, okay? But all I can tell you is what substitution is a little bit more powerful. It's more powerful than elimination in terms of solving for various type of equation. Later on, you guys are going to learn something that consists of non-linear equation. And it turns out that some problems, the elimination method may not work, but substitution will do the job. All right, so you have the two basic methods to solve: substitution and elimination. Okay, let me move on to another example. This time, I'm going to give you a system of 3 linear equations with 3 unknowns. Okay, so it's going to be bigger. It's going to take more time. However, the basic concepts will be the same. Okay, let's move on. Solve for x, y, and z. Okay, let's look for an example. First equation, 5x plus 3y minus 2z equal to 1. Second equation is x minus y plus z, x minus y plus z equal to 6. And the third equation is 2x plus 2y minus z equal to negative 1. So this time we have 3 linear equations with 3 unknowns, x, y, and z. Alright, so as usual, let's make our work easy by giving them names or label the equation. Equation 1, equation 2, and equation 3. Okay. Before we start showing you guys this elimination method and substitution method, let me just point out the core main ideas that we use for solving system of linear equation in here. Our goal is trying to reduce the number of equations and reduce the number of unknowns. In other words, say if you have a system of 5 linear equations, 5 unknowns. You're trying to bring it down to a system of 4 linear equations, 4 unknowns, bring it down to 3, and then eventually 2, and then 1. Then you can solve. Okay? Doesn't matter what. This is what you're trying to do. So let's start with the substitution method. It's number 1. Substitution. All right. What was the idea of substitution method? We're going to choose an equation. We're going to solve for one unknown. And our job is to choose an equation, right? If we be smart, we're going to choose an easy equation and solve an easy unknown. I'll choose equation 2, and I'll solve for x. You can solve for y, you can solve for z, you can choose any equation you like. But let me just choose the first equation. I'll solve for x. Okay? The second equation, I mean. Choose equation number 2 and solve for x. Okay, so I got what? X minus y plus z equal to 6. Of course, solve for x in here means we solve for x in terms of y and z because we have 3 variables. So add y and subtract z on both sides. We're going to have x equal to 6 plus y minus z. Add y, subtract z on both sides. Okay? Now, what do we do after this? We're going to substitute that x by 6 plus y minus z into the other 2 equations. All right? We already used equation 2, so it's gone. It's done. Plug x, and substitute x by 6 plus y minus z into equation 1 and 3. Okay? See what happens. Second step. This is our first step right here. Second step. Substitute x by 6 plus y minus z into equation 1 and equation 3. So let's start with equation 1. Equation 1, we have what? 5x plus 3y minus 2z equal to 1. I will replace x by 6 plus y minus z, so I got 5 times 6 plus y minus z plus 3y minus 2z equal to 1. Simplify. We got what? Factor out 30 plus 5y minus 5z plus 3y minus 2z equal to 1. Now combine the like terms and bring all the numbers to the right hand side. So 5y, 3y is 8y minus 5z minus 2z minus 7z. And subtract 30 on both sides equal to negative 29. You see what we have in here? A new equation, a brand new equation without x in it. See? We have a new equation, no x. So we're down to 2 variables, y and z. And as you can guess, we're going to repeat the same step for equation 3. We're going to end up with another equation with just y and z into it. That's why we say what? Try to bring down from 3 linear equation to down to 2 with just 2 variables. Alright, equation 3, we have 2x plus 2y minus z equal to negative 1. Replace x by 6 plus y minus z again. So 2 times 6 plus y minus z plus 2y minus 2, minus just z, sorry, minus z equal to negative 1. Factor out, simplify. 12 plus 2y minus 2z plus 2y minus z equal negative 1. Alright, combine our like terms. 4y minus 3z equal to negative 13. 2y with 2y is 4y. Negative 2z minus z, negative 3z. Subtract on both sides, negative 1 minus, so it's negative 13. You see what we got in here? We're not done yet, by the way, but we are simplifying our problem from system of 3 linear equations with 3 unknowns. Now it's down to what? System of 2 linear equations, just y and z, with 2 unknowns, y and z. All right? Oh. This is what we ended up right now. 8y minus 7z equal to negative 29. Second equation is 4y minus 3z equal to negative 13. This system is much easier than the original system, and we only have to solve for y and z in here. Alright, of course we learned everything about this already. It's, what substitution or elimination. There's 2 methods that you guys can use to solve. In here I'm going to use elimination because I see 8y and 4y. It's nice to multiply by 2 in the second equation, and it helped me to solve. Alright, so time the second equation by negative 2. You know the purpose of multiply by negative 2. I want to have negative 8y in here, that's why. So 8y minus 7z equal to negative 29. Negative 2 times 4 is negative 8y plus 6z equal to 26. Now add them up. Y cancel out. Negative 7z plus 6 is negative z equal to negative 3. So z is equal to 3. Okay, now we're dealing with system of 2 linear equations, 2 unknowns, just y and z, right? We got z equal to 3, plug them back in either two of those equations, you can solve for y. Alright, let's do it here. 4y minus 3z is 3 times 3 equal to negative 13. So 4y minus 9 equal to negative 13. 4y at 9 both sides equal negative 4, so y is negative 1. So you got y, you got z. You plug them back to any of those 3 equations. You can solve for x, or you can plug it in. Well, x is what? 6 plus y minus z right there. Just look for a equation that got all x, y, and z, and plug in x and plug in y and z. You can solve for x. So x is equal to 6 plus y minus z. 6 plus negative 1 minus 3. So x is equal to 2. And you have a solution. X, y, and z equal to 2, negative 1, and 3. We use the same way to writing solution as we had before. This is a 3 tuple. X is 2, y is negative 1, z is 3. By the way, this is graphically those are not line anymore. The equation represents a plane. You guys are going to see those in calculus 3. You keep moving on. Alright, so the graph you see is going to be a 3-dimensional space, and the 3 planes are going to be intersecting each other at a point. And that point is at x equals to 2, y equals to z, negative 1, and z equals to 3. 3 coordinates. Okay, and not just solving, hopefully, via the example, you see the main idea for solving in here is what? We try to lower the number of equations and try to reduce the number of variables in here. We started with a system of 3 linear equations, 3 unknowns. Okay? We choose an equation. We solve for one variable instead of the others. And we plug into the other equation. In this particular example, I chose equation number 2. I solve for x. I plugged it back to equation 1 and 3. And then when x now replaced by 6 plus y minus z, no more x involving. I ended up with 2 new equations. Okay? Those 2. Right, just y and z. I wrote it right here. See? And we can solve it just system of 2 linear equations, 2 unknowns. The idea is very important, guys, because later on you may not just deal with 2 or 3 system of 2 or 3 linear equations. You may have 4 or 5 or 6 linear equations. And you get the idea, you guys can do the same way. Say if you got a system of 5 linear equations, 5 unknowns, right? And what do? Use substitution. Choose an equation, okay? Choose an equation. Solve for one unknown. Then substitute that into the other 4 equations. You end up with a system of simplify. Okay, you have 4 linear equations, 4 unknown, and repeat the same strategy, same step. Choose 1 equation out of the 4, and then solve for 1 variable, and then plug them into the other 3. You're gonna go down to system of 3 linear equations, 3 unknowns, and then do one more time, till you have 1 linear equation, 1 unknown. Now you can solve. Okay. Next, let me cover the other method of elimination. And keep in mind that it's a different method, but have the same idea. Reduce the number of equations and reduce the number of variables. Okay, let's start with the second method, elimination. Second method, elimination. Now you have to ask yourself, which variable do you want to eliminate, x or y or z? In this example, I'm going to do eliminating z because what? I'm looking at equation 2 and equation 3 right here. I got plus z and minus z. I don't need to multiply anything. All I have to do is what? Add the 2 equations together and the z just disappear. Okay? You can do any equation, choose any pair of equations you like. You can eliminate any variable you like. Say, if I randomly choose 1 and 3, and now I want to eliminate x. See what I can do to eliminate x from here. I see what 5x in here, 2x in there. If I want to eliminate x from 1 and 3, I'm going to multiply the first equation by 2. I got 10x. Multiply the last equation by -5. So I got negative 10x in there. So add them up, x is going to disappear. Just kind of looking for the LCD, common denominator. Okay? Pretty much the same way. Okay, but in here I'm going to eliminate z because it's a lot easier to do and I'll have the same answer anyway, so why make our life so hard? Alright, eliminate z. Eliminate z. Okay, from equation 2, I have x minus y plus z equal to 6. From equation number 3, I have 2x plus 2y minus z equal to -1. All I have to do is to add the 2 equations together. I got 3x plus y, or z cancel out, equal to 5. You see what happened in here? I have a new equations, okay? Just x and y, no more z. And I know that I'm on the right track because our goal, as I would say, our ultimate goal is try to reduce the number of variables. And I need to look for another equation, which is x and y, to solve because I know that we're going to need 2 linear equations to solve for 2 variables. And I already choose a pair of 2 and 3 to solve for z. I have to choose another pair of equations, and I have to eliminate z again, so that I'll end up with a new equation, which is x and y new. Alright, this time I'll choose equation 1 and equation 2. Equation number 1, we have 5x plus 3y minus 2z equal to 1. For equation number 2, I see that I got plus 1y right, oh, I'm sorry, 1z right here, so I'm going to multiply the entire equation by 2, so that I got 2z. After that, I'll add the first equation, the z going to be cancel out, time 2, okay? I got 2x minus 2y plus 2z equal to 12. Multiply everything by 2. Now add them up. I got 7x plus y, z cancel out, is equal to 13. Alright, so I have a new system. 7x plus y equal to 13, and 3x plus y equal to 5. I see that we have a much simpler system of linear equation, only 2 variables with 2 unknowns. And of course in here I'm going to do elimination again, alright? I see y, so I'll just simplify the y. You can think of it this way. Use the first equation, subtract the second equation, you can solve. Be consistent with what the book writes. So